Hello everybody and welcome to today's video. Today we will focus on two new topics. Well, they're kind of new, kind of old, and those are maxima and minima. So you might have heard these words before, you might already have inferred what these two mean, but if you don't worry, I'll explain everything to you. So today we're going to discuss the difference between a local minimum or maximum, so minima or maxima, or the absolute value of them, as well as what critical numbers are and how they are used to help us with functions. So let's get started on that. So local versus absolute maxima and minima. So here are a few definitions that we need to know before we go into actually solving some problems, and those definitions are the following. Given the graph of a function f of x, a point is a local maximum if the y-coordinates of all the points in the vicinity are less than the y-coordinate of the point. So what does that mean? So if you look at a single point, if the area beside it is less than the point itself, then you have a local maximum. Algebraically, if you want to prove this, you would have to find f prime of x. If it changes from a positive slope to 0 to a negative slope, then you would see that that point is a local maximum. So again, as f prime of x changes from positive to 0 to negative as x increases, from x less than a and x greater than a, then the point a, f at a, is the local maximum. That sounds a little bit complicated, but don't worry, I have an example on the next page to showcase this exact idea. Similarly, if you want to find what a local minimum is, you need to find the y-coordinates of all the points in the vicinity, right, and see which one is the smallest, right? So if you have a very small point and everything else around it is greater than it, then that is your local minimum. So again, if you want to prove this algebraically, you'd have to see how f prime of x changes. So if f prime of x changes from a negative slope to 0 to a positive slope as x increases between 2 points, then the point at a, f at a, is the local minimum, and a is the local minimum value. So now that we know what a local minimum and a local maximum are, we could talk about what the absolute minimums and absolute maximums mean. However, if we want to be very specific, any type of local maximum or local minimum will be called a local extreme value, a local extrema, or a turning point. These three definitions or these three terms are very important for you to understand because the remainder of the chapter will follow these terms. But again, if we want to talk about what an absolute maximum is and what an absolute minimum is, well, those are just the toppy tops, like the very high points that you could find, right? The absolute maximum is the maximum point that you could get to on your function. Sometimes it might not exist because your function will approach positive infinity, or for example, if you have an absolute minimum, it could also not exist if you approach negative infinity. But either way is just either the highest number or the lowest number of the graph. So using the definitions we just saw on the previous slide, let's try to do this very simple example. So over here, we're given the graph of the function f of x, right? And we have to find out its local minimum, local maximum. We need to locate any in-common characteristics between the local maximums and the local minimums. And then we also need to identify the absolute max and the absolute minimum values in the given interval. The interval in this case is of course how big the picture is. We don't see any arrows coming off of the graph, which we could conclude is where the interval has ended. So let's quickly run down from the solution. The local maximum, the local minimum is the first one we were given. So the local minimum would have to be B and D, right? How would we know that? Well, let's look at the areas around these points. As you can see here, all the values are greater than D, right? D is the smallest value within its region. Similarly with B, on this side we're going up, and on this side we're also going up, which would make B a local minimum. Similarly, when we're talking about a local maximum, those would have to be A and C. Again, A is the largest value in its area. These values here are all smaller. Similarly with C, on the right side it's smaller, on the left side it's smaller, which would make C also a local maximum. So what are the common characteristics of these 4 points? Well, if we refer back to the previous slide, we know that when something changes from positive to 0 to negative, we have a local maximum. And here, when it changes from negative to 0 to positive, it is a local minimum. So the 2 definitions have in common the following, right? It's f prime of x and 0. So what does that mean? Well, if we have the derivative of x equal to 0, that would mean that the slope of the tangent is 0, right? So it's a horizontal line. And because of that, we can actually see that every single local maximum and local minimum value will have a tangent that is horizontal. Moving on to the last part, we need to identify the absolute maximum and the absolute minimum values. So this one is super easy. The biggest point on this graph, the biggest value would have to be f, right? Because it goes above a. And similarly, the smallest point on the graph would have to be point D, right? Because E is greater than D, B is greater than D, and then we already said that these are local maximums, so therefore they couldn't really be the local minimum, like the absolute minimum, right? And for that reason, the lowest point on the graph is D. So all of that was pretty easy, right? Like you could easily look at a graph and identify any local maximum, local minimum, a maximum, or an absolute max or an absolute min. However, it gets a little bit more complicated when you can't really see the function you're working with. For example, if you were given just the equation of a function. We did learn how to graph functions in grade 12 advanced functions. However, if you recall from that class, we never actually figured out how high something should go, right? Because it was very difficult for us to estimate how high a point would go in between 2 zeros or 2 roots. So luckily for us, with the help of derivatives, we could figure those things out. As we saw from the previous example, so the graph, we know that local maximum and minimum share one common property, and that is their tangents are horizontal. We know how to figure out a tangent, right? We've learned how to find the first derivative of a function, and so now we know that if we find the roots of the first derivative of f of x, we'd be given the point at which the slope is equal to 0, and thus that would be our local maximum or our local minimum. So those roots are known as critical numbers or critical points. So what do we do with those? Well, if we were to find out the value at a, or the value of x, for when these critical numbers occur, so when f prime of x is equal to 0, we could figure out the local maximum or the local minimum by simply plugging it back into our equation. So let's quickly do the following example. So we're given the function, this one here, I'm not going to try to read all the terms, and we need to determine its critical numbers, any local extrema, so remember that's either the local maximum or the local minimum, or both. Now we need to find the absolute extrema in the given interval. So let's quickly move over to notes so I could do this example for you. Okay, so I copied over the question to notes. Now we could go ahead and solve it. So what do we need to find first? Well, the critical numbers, right? As I said before, to find the critical number, you need to find where f of x is equals to 0. In some scenarios, you might have to find where f of x doesn't exist, but those cases more often or not occur with piecewise functions and rational functions, which is not the case with this example here, because as you could see, it is a polynomial equation, right? So in our case, we just need to find where f prime of x is equals to 0. To find f prime of x, we just need to take the first derivative. So f of x let's copy it down, is equals to 2x cubed minus 3x squared minus 12x plus 5. So using our derivative rules, we know that f prime of x would be 2 times 3 is 6, x squared, 2 times 3 is again 6, but now it's x. Negative 12x is the same as negative 12. So this is our equation for the first derivative. Now let's find out where it equals to 0. Right, to do that, we need to factor our equation. So f prime of x, if we factor it, we could factor out the 6, we get x squared minus 6 minus, x squared minus x minus 2. So now, does this factor to anything? Well, you could use which other method you remember, or maybe you could already visualize what the answer would be. I am the former, I could tell what it will be, and that would be x minus 2 and then x plus 1, right? Because this is negative 2 and this is negative 1. So what adds up to negative 1? Well, you could be negative 2 and 1. What multiplies to negative 2? Negative 2 and 1, and so this is our answer. From here, we know that we need to get this to 0. So we know 0 is equals to 6x minus 2, x plus 1, and so x could equal to 2 or x could equal to negative 1. So we have found the critical numbers for our example, right? Now we need to identify our local extrema, right? Which would be either our local maximum or our local minimum. So you could possibly just substitute those in, right? What is f at 2? Well, that would be 2 times 2 cubed minus 3 2 squared minus 12 times 2 plus 5, right? We could put this into our calculator and then we should get 0, right? Not 0. This would be f prime at negative 2 at 2 was equals to 0, but f of 2, it would be negative 15. Sorry, I didn't look at the right place. But here we have negative 15. But can we prove that this is a local minimum or a local maximum? No, we can't, because we don't know if the numbers beside would be negative 16 and negative, for example, 16 again, right? Or if they would be like negative 14 and negative 14, because these two would give us completely different outcomes, right? If it was negative 16, this would mean this is a local maximum. If this was negative 14, that'd be a local minimum. So how do we check out which part is correct? Well, the answer is quite simple to that. We could actually just make an interval chart for every critical point that we know. In our case, we only have 2, so we shouldn't need a lot of different test values. Our first test value would have to be something that is less than negative 1, right? So let's put that, x is less than 1. Then over here, we could put x is equals to 1 if you want to. You could also put it over here, right? If you want to do that and save some space, but just so we are thorough with our examination, I will do it this way. Over here, you could technically write x is greater than 1, but we also know that x is less than 2, right? For our second part. And therefore, we could combine these two together and we would get that x is greater than 1, but x is still smaller than 2. Then we have x is equals to 2, and our last one is that x is greater than 2. We could try out different test values. You could put your test values here, so let's put this test value. For example, this would be negative 2. We know that in negative 1, it'd be negative 1, right? That's the only test value we could get. This would be 0, this would be 2, and this could be 3. Very simple. Now, let's look at how f prime of x behaves. The reason why we're going to look at f prime of x is because if you recall by our definition, we need to see that the slope is going from a positive to 0 to a negative for it to be a local maximum. And then it needs to go from a negative to 0 to a positive for it to be a local minimum. So now with these test values, we could actually see whether or not we have a local max or a local min. So if we substitute negative 2 into our equation, we would get 24, which is of course a positive. Negative 1 is one of the zeros, which is of course going to give us 0. Then at f at 0, the only thing that we have would be our negative 12 over here, right? So it's negative 12, Then over here we are at 2, which is again a 0 because that's one of the factors. And then at 3, let's substitute that in, and you will get 24, which is a positive. So we have a positive going to 0 to a negative, which would tell us that f of x was increasing, right? Then it was our critical point, which if we substitute -1 into our original equation, you get 12. So we have the point -112, and then our function was decreasing. Then over here, we know that we already calculated be 2, sorry, not 2, not 0, it's 2, -15, that's our other value. And then for our last value, we are given x is greater than 2, so let's substitute 3 in, and you'd see that it is indeed plus, and which would mean it's increasing once again. So, increasing. There you go. So what can we form from this chart? Well, the answer is quite simple. Starting from f prime of x, you could already have figured out which one was the local max and which one was local min. Over here, we were going from a plus to a negative, which would make that a local max at -112. Then over here, we were decreasing to increasing, or from a negative to a positive, which would mean a local minimum at x is equals to 2, so at 2, -15. So this is the procedure you need to go through to figure out a local maximum or a local minimum. For part C, our question asks us to find the absolute extrema of f of x in the following interval. So that is pretty easy to do. So first of all, let's find the absolute minimum. So again, if you just want to quickly sketch out the graph, it would look something like this. The idea would be is that either this point or this point here would be the minimum, right? Because from here we know that we were increasing, which would mean we would start at a small value, right? Then we also got to our we got to our local minimum, which was to -15. So we need to compare if this low point is smaller than our local minimum. The way to do that is quite simple. If that point was smaller, then at that region, right at the end of right at the start of our function, so at the start of our interval, we'd have a really small value. So let's plug in f at 2. We did that before, right? And then we got -15. So luckily for us, we were actually looking at our region right here. This is the starting point, and everything else beyond it is increasing. So therefore, our absolute minimum will have to be 2, -15. Our absolute maximum is a little bit difficult to find if you don't have an eye for it, but I'll assure you it's pretty simple too. Again, if we look at the graph, we have a maximum here, and then we go up. We know that because over here it was said to be increasing then decreasing, so this is a local max as we already found out, but we're also starting at a local minimum and then going up. We're gonna go up until we reach positive infinity, which will never happen, so technically we don't have an absolute max because it will reach positive infinity. But if we actually look at our interval, the maximum value you could go to is when x is equals to 4. So let's see what f at 4 is equals to. Well, f at 4 is actually equals to 37, which as we know is much bigger than 12, right, to the point over here. And that would mean that our absolute max is actually at 437. So by comparing the different portions of the graph to one another, we could figure out where the absolute min and the absolute max are present. Again, you could either sketch a small portion of the graph like this, so you could visualize which points you would have to compare, or you could infer what these mean. If you're increasing from something, right, that something was probably very small at one point. So if you find the absolute minimum, you should evaluate that point and compare it to the local minimum you've already found. If you were starting at a local minimum and you kept increasing, you're going to go up to a very high value. So now you need to compare how high is this value compared to your to your local maximums. So hopefully that little procedure made sense to you and how we found out those answers. So with that example being done, we are now on to the homework. I have assigned only 4 questions. They're very similar to the questions that we've done today. All you need to know is how to find the first derivative and how to apply your understanding of horizontal tangents to figure out what is a local maximum or minimum, as well as how to figure out what an absolute maximum or minimum is pertaining to the critical points that you have found previously. Again, I'd like to thank anybody who has stuck around for this video. Hopefully I've cleared up some issues that you might have had in this chapter, as well as helped you learn new material. It's so much fun helping you guys. So again, thank you for watching, and I can't wait to see you guys next time. Bye bye.